All right, the limit comparison test is very similar to the direct comparison test. If the inequality piece is kind of giving you a hard time, this is going to be very similar where you find like that parent series that you're looking for, but you can use limits in order to find convergence and divergence versus comparing it overall with inequalities. So here is our limit comparison test. If you end up getting a sub n and you know one of them converges, okay, and the other one diverges, and you get that limit as n goes to infinity of the two series goes to a number that's not 0, then either they both converge or diverge. If that limit does go to 0, okay, then they converge. If it goes to infinity, then they diverge, okay? So let's look at what that looks like in practice here on this first one. So again, I see 1 over square root of n plus 1. So I'm going to say here that I'm going to use the series 1 over square root of n, which I know diverges by p series. All right, so I'm going to say take the limit as n goes to infinity of my a sub n over the function, or the series I should say, that I know converges or diverges. Well, that's the same algebraically as 1 over square root, draw that a little bit nicer here, plus 1, and then I'm going to multiply by the reciprocal. And so that's the limit as n goes to infinity of the square root of n over the square root of n plus 1. Now that is 1, which is not 0. And so I know that because 1 over square root of n diverges, that this is also going to diverge. And you would keep all of that work there in order to show that. All right, so if you look at part B here, this is one that like that inequality might just get really messy, or you might be like, how do I set this up? But I know that I see something that models a geometric series of 2 to the n over 3 to the n. Which would be the geometric series 2/3 to the n, which I know converges. Okay, so let's look at this. If I take the limit as n goes to infinity of 2 to the n plus 1 over 3 to the n, and then I divide that by my b sub n. Let's multiply by the reciprocal. My 3 to the n's would cancel, and I would be looking at the limit as n goes to infinity of 2 to the n plus 1 over 2 to the n, which equals 1. And so by our definition up here, okay, that's a limit that's not 0, so they either both converge or both diverge. So since this is not 0, this must also be convergent. All right, let's go ahead and look at our natural log over n squared for our last one. Now again, this might be one that you're like, I'm not quite sure what this needs to look like. I do know that like natural log of n is always smaller than n. We talked about that last time, right? Like the natural log of n is always smaller than n. So if I divide both of those by n squared, maybe it makes sense for us to look at like 1 over n on this side over here. So let's look at the limit And I know that diverges, right? Okay, natural log of n over n squared, all over 1 over n. I'm going to multiply over here. I end up getting the limit as n goes to 0 of those cancel the natural log of n over n. I can use L'Hopital's rule, and that's going to end up going to 0. Well, let's check our rules, okay? What did it say if it goes to 0? Okay, if it goes to 0, then only if B sub n converges, then A sub n converges. So that's not going to be helpful. That's going to be indecisive there. But let's maybe check out something that converges. Okay, let's just see. All right, so limit as n goes to infinity of this over 1 over n squared. I multiply by the reciprocal. Oops, reciprocal would go this way. These cancel. Well, that goes to infinity. Okay, and then that also doesn't provide me any information. So let's maybe try something that's between these two. Maybe if I do n to the 3/2, which I know converges by p series. So that's going to be the limit as n goes to infinity, natural log of n over n squared, and then I'm going to end up multiplying by the reciprocal. That gives me the limit as n goes to infinity of the natural log of n over the square root of n. And then when I use L'Hopital's rule and evaluate this, I do end up getting 0. So now let's go back up to these rules and let's make sure. If that is 0, then if one converges, the other converges. I can use that rule and get convergence. So you can see here, sometimes you have to use a couple of them and kind of go around some things that you know in order to get one of these rules for limit comparison to work. Sometimes it's nice and easy, like these ones here, okay? But this again is a different, direct comparison, limit comparison are very similar, and you can kind of use them interchangeably. This one helps when you don't necessarily want to look at the inequality statement and you want to do just an evaluation of what the limit does as n goes to infinity. Then the limit comparison is going to be your friend here, okay?